associate professor of WCBM Chemical Science Engineering at the UIUC and the director of Game Lab. He received his degree in ECS from Seoul National University of Korea. He was a postdoctoral fellow at the Robotics Institute at Bimanual University for DARPA Robotics Challenge and a research scientist at Disney Research, and he also developed the bifield working controllers for humanoid robots at Samsung. His research interests include humanoids, robot design and control, motion learning on hardware, and safe human-robot interaction. Please welcome Professor Joohyung.
Thank you. Thank you for a nice introduction. And I'm actually really sorry and I couldn't be there in person. Well, today's topic is I just wanted to introduce what I'm doing now based on my history of the research. And the title is The Return of Teleoperation in the Age of Embodied and Physical AI. So this is my intro. So I've been building many systems, although I've been always with ECS. Currently, I'm with the ACE and AI school at KAIST as a adjunct professor. But I started like a humanoid robot back in 90s, so I had to build everything from scratch at that time. So in my graduate school, late 90s and early 2000, a biped robot is mostly based on the developing the system itself and developing the working algorithm. So I worked on that for quite a long time, even in Samsung Electronics. Samsung Electronics now Samsung has the humanoid team, but back in 2008, 9, 10, Samsung had a really nice team worked on this robot array, and this is a Symbiocon-based RL walking we made in 2009. So I made some contribution in this walking robot. And in 2012, I got really interested in participating in DARPA Robotics Challenge. So I moved to US to participate in the DRC and worked with Chris Atkinson in CMU as a team member in WPI CMU team and developed this whole body controller. So this is an early version of the MPC-based online hierarchical optimization-based approach for the whole body controller. And then I moved on to Disney Research to work on interesting character features in the character, like Pooh's hugging or Tigger's hopping, or some other features for Disney's future use in theme park. And so it's these examples are mostly system-based, like developing the new feature of the interesting characters. But my main job was actually motion retargeting from the animation character or movie characters motion to the animatronics in the theme park. So my work was the motion retargeting and developing this kind of animation characters feature in using the robotics technology there. And in 2020, I moved on to academia, joined UIUC, and now working on some other stuff. So I wanted to introduce that one. So after spending time to develop humanoid robot, I really wanted to do some research, but very practical one. So I wanted to add arms everywhere. So my solution was something like this. I already developed some reconfigurable robots like a Snapbot or some other robots which can change the configuration based on the modular parts. And for the manipulation, what I started was this plug and play robotic arm system. So if we have good like design to, well, let's just watch the video. So this arm was plugged into the kitchen between the dishwasher and the sink. And then we can easily unplug this like that. So the problem of the current commercialized arms is very expensive, and the real problem is once we install that on some place, it's very hard to move. It should be bolted down somewhere. So I wanted to develop something based on the standard that is mount. If we can just provide power and the communication, we can use the arms, not just this arm we developed. If we have the same protocol, we can actually use any arms. If we have good like interface like a USB port. What USB port is doing is powering the device and just providing the communication channel. It's just like that. If we can have sturdy enough structure to hold the arm, then we can use this human size arm to do some task up to like not quite human level, but if we can have up to like 3 kilo, 4 kilogram payload, then we can do many tasking at home. So that was the goal. So we developed 6 degree of freedom, 7 degree of freedom arms with slightly different scale, including the gripper and the RGBD camera under 6 kilograms. So we are using this a lot in my lab. So it's not just for the fixed structure. If we can attach that docking mount to a mobile robot, we can actually transform any robots to as the mobile manipulator. So the top left one is this just a dinner table, or top right one is a tea table. We can do the chess playing with the one arm, where we can transform the vacuum robot or the restaurant serving robot as mobile manipulator easily, and that can use the feature of the mobile base for the robot. And well, I made this slide like 4 years ago, before the GPT era. Because I've been working on this motion retargeting a lot, I started using the task retargeting as some concept for the task solutions. So at that time, I thought we already have good like natural language process and computer vision. So if we can utilize that kind of thing, we can easily generate the very top level the sequence for the robotics function. Then the problem we need to solve in robotics field is how to find the optimal or the proper configuration and the physical interaction between the robot and the object to do the task. So I wanted to focus on the far left like solution, and the top right one, it's the configuration. So the challenges is robot configuration and skills and real world experiment at the time. So my solution for the robot configuration was the arm we developed. And we actually made this like fully autonomous like environment using our arm, using different like furniture and the environment. So based on the location, robot has its solution about what to do in that location. So it's working pretty well. It's not using any like a data-driven method, but just using model-based one. It was okay. The problem is every time we add the location, the application, we needed to make the new solution for the task, and that was kind of time consuming and tedious, and wanted to that part also automated. So we started to explore the teleoperation. So teleoperation is really interesting technique because it's a very long-standing proven technique. So I'm still a big fan of Disney, and this is Walt Disney's old video. Walt passed away like 1966. So this was taken 1964 or 63, and at that time, well, Disney already had the wireless teleoperation for the humanoid robot like this. So using just radio frequency, but with the potentiometer, but it's pretty working pretty well. So the the person is actually controlling this animatronics humanoid shape real time. And the more interesting part of this video, Disney actually collected all the data for the show. So it's just a replaying, but that's really interesting. Like fact they use the data for the robot motion, well, animatronics motion for the show. And the teleoperation is related to dimension reduction and the data representation. This part is really important. So this is another like a video. I really like animations and all this kind of thing. So this is old animation, and interesting the part of this scene was the main character is controlling whole body robot with just a 3 lever, meaning he's controlling the robot with 3 degree of freedom interface there. And that doesn't make sense because usually humanoid robot has at least like 30 degree of freedom, like 6 or more for the each limb and well, heads and the torso. So using just a 3 lever for the whole body control doesn't make sense. But if you think about, so this is the standard process for the biped walking. People are using learning-based method a lot for now, but the research is still using some part of this kind of process. So for the biped locomotion, we usually need the footstep planner first to know where to step on the ground. And based on that, we can plan the COP central pressure trajectory, which is the stability condition for the walking. And after that, researchers are usually using the reduced model to get the COM trajectory in 3D, like inverted pendulum model. And based on the previous condition, the target COP trajectory, we can actually get the solution for the COM trajectory using this kind of template model. Then using this, like all the information, we can solve the joint state using this COP and the COM and everything. You don't need to understand what's going on here, but the interesting part of this is if you think about the dimension of all the representation in each step, the footstep on the ground with left and the right leg, right foot is 260 degree of freedom like representation, and the target COP trajectory is actually 3-dimensional on the foot. And the COM trajectory generation is 6 degree of freedom in just a 3-dimensional, just the position and the orientation. And the actual solution for the dynamics is, well, if we assume the robot is 30 degree of freedom, then it's about 100-dimensional space. So this kind of process is actually dimension mapping to make the problem easy in the reduced dimensional space, then find the actual dimensional space solution for the motion. So that's why we can use this like just two analog stick to control the characters in the game. And teleoperation allows the exploration of which modality need to be added. So robot's perspective on the world is actually very different from what we have, because as a robot has different configuration, different morphology, and the different sensors. This visualization is actually for the human users, but what robot is seeing is very different. So I had a chance to ride on a giant robot. This was just a 4-meter high humanoid shaped robot, just a scaled humanoid. And it was very scary experience. But when I did this, I actually wore the GoPro on my head. So this is the video from the GoPro. The reason why I wanted to share this is so now robot is walking like this, but I cannot see anything but some like POV here. I couldn't see the robot's foot or hand. So meaning, even though this one has similar morphology, just as scaled, the location of sensor or when we design the sensors, when we design the perception, we actually need to consider everything pretty well, and then need to scale the problem, and also need to consider the resolution. And uh, meaning the like design should be different based on the morphology and the scale. So teleoperation actually can explore all this kind of space when we collect the data via the robot's embodiment. So we developed this PAPL, which is also plug and play robotic limb environment for this modular system. So we have this plug and play robotic arm system to explore different morphologies. And we can also use the same docking mount to control everything, but with scaled the leaders or different leaders, like a VR system or the joysticks to control the robot by this dimension mapping. So teleoperation system. So this is an overview of the teleoperation system we developed. We can use any kind of leaders for the manipulation. This is just for the manipulation. So if the robot and the leader's configuration are different, then we are using the task space control. And if the configuration is same, just a scaled, then we can use joint space and check some safety and solve the inverse kinematics if the configuration is different. Then we can get the joint state. And we can use any the target followers in simulation or real world. The interesting part of the PAPL is actually we have this feedback. So all the like teleoperation system has feedback based on the robot sensors, but this one is slightly different. So we have intrinsic feedback and the extrinsic feedback. And the intrinsic feedback is more like the way to actually induce the virtual force, like gravity compensation or some kind of neutral force to the system. So the leader in this leader, the leader is just based built with the very affordable motor. So the motor doesn't have enough power to the gravity compensation, but it can uh, uh, generate some force for the system. So intrinsic feedback is like when we are using the analog stick in the joystick is always spring loaded to the neutral point. It's something like this. So if we have some kind of neutral pose for the target task, we can make that happen for the user interface. Also, not to make this high dimensional like leader to be collapsed. Oops. And the extrinsic feedback is also giving some feedback to the user, but not based on the sensors from the follower. So we are only using the difference between the user's motion and the follower's motion, leader's motion and the follower's motion. Meaning, so in this video, the operator already closed fully the gripper, but because of the cup, the leader's gripper couldn't be closed. In that case, there's a difference, right? Then we can give feedback to the user. So it's not based on the touch sensor, but just the difference. So in this case, human motion is usually much faster than the robot's motion. So the operator moved faster than the robot's maximum speed. So there's a difference. The shade, the red shade is actually the just based on the leader's motion. In this case, we can generate some kind of feedback to the operator to know what's the status of the robot without like just seeing that. It's very hard to see the difference for the operator. The first feedback were some kind of different different like modalities. Feedback is actually really important. So yeah, we can do the same thing based on the test control. So this is the very simple tabletop task, bimanual task people are doing a lot. So we are using the our system for this. And we have two kitchen mock-up in my lab. We can use scaled like system just like that, or we can use this similar setting for the user to know the actual movement. Or the spot bimanual like system controlling this. And we can also use our software pipeline for the commercialized robot. And we can use different leaders for the same arms or using VR systems. Because most of the VR system is providing the wrist pose, so we can use that wrist pose for the control. Well, in the same manner, we can also use the UMI, recorded UMI. This is not on the policy, but just a recorded UMI data and replay that one using our pipeline. So we also developed the humanoid version of the PAPL. So if you are parents, you know how to control the baby. So baby carrier is a pretty good interface because adult workspace is always includes the baby's workspace is a actually very good like interface to control the human shape. So we developed this child the controller for humanoid imitation and live demonstration for the humanoid robot. So to control the all four limbs, we need four hands, four arms, right? So local manipulation is not straightforward. If you watch this uh, Tom Wright movie carefully, the operator is using right leg for the locomotion and then change the mode for the bimanual manipulation, then change the mode back to the locomotion mode to control the so the mapping can be defined by any users to do this kind of task. Okay.
I think we're out of time, Joohyung.
Okay. Oh, I I didn't. Can I use 1 more minute?
Sure.
Sure. What I'm doing is I'm currently exploring the data diversity, not quite trying to develop model now, but I wanted to share some vision in my point of view. Everyone knows what is the history and prehistory, and the writing system is the key of the we call the history after we have this writing system. But before, in prehistory, we already had this word and the action. And based on the human's perception, we actually perceive the word. And then people develop this language and the symbol, all this knowledge and the math and science. But if you think about the data representation, the dimension of the word, we actually don't know the actual dimension of the word. We only use our like perception capability to actually feel the word. Then based on then we develop this writing system. Then during information age, what the human mankind developed is actually decoding and encoding system to reduce this abstract like data even more. So for now, what we can do is decoding the language. Then the next step we want to do is adding some other like perception modality or some other like dimensional information. We want to decode the action. Then probably we will like do some more based on the different sensors like superhuman sensing perception capabilities. I think that this is an important like concept we need to know because I am not like a true believer of the like data-driven method that can solve everything, but in this action space, we actually don't have enough data now. So I really wanted to share this thought in this talk. Okay, sorry about the time, but yeah, that's pretty much